All right, let's talk about one of the biggest, most powerful ideas in all of physics, statistical mechanics. At its heart, it's really all about building a bridge that connects the tiniest, most microscopic world of atoms to the big, messy, complicated world that we see and live in every single day.
So let me ask you this, because this is really the core question here. How do trillions upon trillions of, well, mindless atoms just bouncing around randomly somehow come together to create the complex, predictable world around us? Things like the air in your room or a magnet sticking to your fridge. How does all that order just emerge from total chaos? It's kind of funny to think about now, but back in the 19th century, this wasn't just a philosophical question. Scientists were in the middle of this huge, bitter fight over whether atoms were even real. Were they actual physical things, or just a handy little trick for doing calculations? People got really, really heated about this. And right into the middle of this firestorm steps this Austrian physicist, Ludwig Boltzmann. And he has this truly revolutionary idea. He says, look, forget about trying to track every single atom. You can't. It's impossible. But what if you don't have to? What if the key is just to use statistics to figure out what they're doing as a group? For physics at the time, this was a totally wild out there concept. So this was the fundamental puzzle that Boltzmann was trying to solve. You've got the macroscopic world, the world of temperature and pressure that we can actually measure, and then you have this completely invisible microscopic world with just countless atoms buzzing around. How do you connect them? How do you possibly build a bridge between those two realities?
Well, the answer comes down to one single, unbelievably important number, the Boltzmann constant, which we just call K. You can think of it like a translator or a conversion factor. It was the first thing that really connected the micro world to the macro world. It's the literal bridge that relates the average energy of all those tiny particles to the temperature of the whole thing.
And I mean, just look at how ridiculously small this number is. That's a decimal point followed by 22 zeros. What that tiny, tiny value is screaming at us is that the energy of one single solitary particle is just nothing compared to the energy scales we deal with in our everyday lives. It just shows you the massive, massive gap between the two worlds we're trying to link.
Okay, so you've got this radical new idea. Where's the first place you tested out? Well, Boltzmann and his peers started with something simple, something all around us, gases. And this whole statistical approach gave them a completely new lens to understand the very air we're breathing.
And here is the big aha moment. Before this, temperature was just a number on a thermometer. But this new kinetic theory showed what temperature really is. It's not some weird, abstract property. It's just a measurement of the average motion, the kinetic energy of all those little particles. Hotter just means the atoms are jiggling around faster. Colder means they're slowing down. It's that simple. This chart right here, the Maxwell-Boltzmann distribution, it's the perfect picture of this idea. It shows you that in any gas, not all the particles are moving at the same speed. Some are fast, some are slow. But as you heat things up, see that blue curve? The average speed shifts to the right. It gets faster, and the whole range of speeds gets wider. And Boltzmann's constant, K, is the magic ingredient that lets us predict these curves perfectly.
Okay, so this statistical thing works great for a simple gas. But can it handle something trickier? Something more complex? Like, say, a magnet? To really push the limits of the theory, physicists came up with a clever little model to test it out. It's called the Ising model, and you can honestly think of it as a physicist's little toy universe. It's just a grid, and on each point of the grid, there's a tiny magnet, or a spin. And each spin can only do one of two things, point up or point down. The only rule in this entire universe is that each little spin wants to align with its neighbors. That's it. Super simple. So the whole point of this model is to ask a really deep question. It's the same one we started with, really. Can this one incredibly simple local rule, just try to match your neighbor, can that create the huge coordinated behavior we see in a real magnet, where trillions of atoms all line up together? Can tiny local rules create big global order? And the answer turns out to be a resounding yes. On the left, you can see that when the temperature is high, the system is just pure chaos. It looks like static on an old TV. There's no overall magnetism. But look at the right. As soon as you cool it down past a certain point, order just appears out of nowhere. The spins start lining up, creating these huge patches, these domains of up and down. This amazing moment has a name. It's called a phase transition.
And it's the exact same thing that happens when water freezes into ice. You make one small tweak to a big picture property, the temperature, and it causes this sudden, dramatic change in the entire system structure. And the model shows us how that beautiful complexity can bubble up from the absolute simplest of rules.
So all of this brings us full circle, back to the legacy of the man who kicked this whole revolution off, Ludwig Boltzmann, and how his ideas were, in the end, literally set in stone. Now here's a fun piece of history for you, a little twist in the tale. That quote is from Max Planck, another absolute giant of physics, and he points out that, yeah, we call it Boltzmann's constant, but Boltzmann himself never actually used the letter K or wrote it down in its modern form. It was actually Planck who first gave it its symbol and nailed down its precise value. But Boltzmann's true legacy, the absolute heart of his entire worldview, is captured in this one elegant equation. It looks simple, but it's one of the most important equations in all of science. S on the left is entropy, which you can kind of think of as disorder, and W on the right is the number of all the different microscopic ways you can arrange the atoms to get that amount of disorder. And what's sitting right there in the middle connecting them? Our bridge, the constant K. This one idea, this one equation, was so profound, so central to his life's work, that it was carved right onto his tombstone in Vienna. After spending years fighting people who said his ideas were wrong, this was his ultimate vindication. It's the cornerstone of all of statistical mechanics, the final, perfect bridge between the hidden world of atoms and the world we all see. And that leaves us with one final, big thought to chew on. If studying the statistics of simple little parts can explain gases and magnets, what else could it explain? Could we use these same exact principles to understand how billions of neurons firing in our brain create consciousness, or maybe even the complex patterns that emerge in human societies? The bridge that Boltzmann built, well, it might lead to whole new worlds that we're only just now beginning to explore.